Hi everyone, Dr. Zaid is here. Welcome to my learning channel on statistical education. It is a continuation of my previous lecture on rules of counting sample space. In this lecture, we study important counting rules used in probability. These rules help us determine the size of the sample space without listing every possible outcome. The main rules we will use are the multiplicative rule, permutations, and permutations with repeated objects. These rules are widely used in probability, statistics, and combinatorics. In the following slides, we will solve several examples to illustrate how these counting rules work in practice. In this problem, a 22-member club needs to elect 2 officers, a chair and a treasurer. Because the 2 positions are different, the order of selection matters. Therefore, we use permutations. Mathematically, we compute 22p2, which is equal to 22 factorial divided by 22 minus 2 factorial. This simplifies to 22 multiplied by 21, which equals 462 possible ways to elect the officers. In the next problem, we have 4 boys and 5 girls sitting in a row, and the boys and girls must alternate. Since there are more girls than boys, the only possible pattern is girl, boy, girl, boy, girl, boy, girl, boy, girl. The 5 girls can be arranged in 5 factorial ways, and the 4 boys can be arranged in 4 factorial ways. The total number of seating arrangements is 5 factorial multiplied by 4 factorial, which equals 120 multiplied by 24. Therefore, there are 2,880 possible arrangements. In this example, Zaid is assembling a computer and must choose different components. He has 2 choices for chips, 4 choices for hard drives, 3 choices for memory, and 5 choices for accessories. Using the multiplicative rule, we multiply the number of choices for each component. So we compute 2 multiplied by 4 multiplied by 3 multiplied by 5. This gives a total of 120 different ways Zaid can assemble the computer. Now we move next for further real-world problems, solving using these rules. In this problem, 3 awards are given to 25 graduate students. The awards are research, teaching, and service. Since these awards are different, the order matters. Therefore, we use permutations. We calculate 25p3, which means 25 factorial divided by 25 minus 3 factorial. This simplifies to 25 multiplied by 24 multiplied by 23. The total number of possible selections is 13,800. In this example, we choose a president and a treasurer from 50 people under different restrictions. First, if there are no restrictions, we compute 50p2, which equals 50 multiplied by 49. This gives 2,450 possible choices. Second, if Person A will serve only if he is president, we consider 2 cases. In the first case, A is president, and there are 49 choices for treasurer. In the second case, neither officer is A, so we choose 2 officers from 49 people, which gives 49p2 equal to 49 multiplied by 48. Adding these results gives 2,401 choices. Third, if B and C must serve together or not at all, there are 2 ways for them to occupy the 2 positions. If neither serves, we choose 2 officers from the remaining 48 people, which gives 48p2 equal to 48 multiplied by 47. The total number of selections becomes 2,258. Fourth, if D and E cannot serve together, we subtract the cases where both serve from the unrestricted total. Since they can occupy the 2 positions in 2 ways, we subtract 2 from 2,450, giving 2,448 possible choices. In this example, 10 players stand in a row, but we only distinguish them by class level. There is 1 freshman, 2 sophomores, 4 juniors, and 3 seniors. Because some players belong to the same class level, we use permutations with repeated objects. The formula is 10 factorial divided by 1 factorial times 2 factorial times 4 factorial times 3 factorial. After calculating this expression, we obtain 12,600 different arrangements. Next, we consider permutations of the letters in the word infinity. The word infinity contains 8 letters. The letter I appears 3 times, the letter N appears 2 times, and the remaining letters appear once. When objects repeat, we use the permutation formula with repetition. The number of distinct permutations equals 8 factorial divided by 3 factorial multiplied by 2 factorial. After simplifying this expression, we obtain 3,360 distinct arrangements. We now form 3-digit numbers from the digits 0, 1, 2, 3, 4, 5, and 6 without repeating digits. For part A, the first digit cannot be 0, so we have 6 choices of first digit. After choosing the first digit, 6 digits remain for the second position, and 5 digits remain for the third position. Therefore, we compute 6 multiplied by 6 multiplied by 5, which gives 180 possible numbers. For part B, the number must be odd, so the last digit must be 1, 3, or 5. This gives 3 choices for the last digit. The remaining positions give 5 choices for the first digit and 5 for the second digit, resulting in 75 odd numbers. For part C, when we apply the restriction that the number must be greater than 330, the total count becomes 90 numbers. In the final problem, 3 lottery tickets are drawn for first, second, and third prizes from 40 tickets. Since the prizes are different, the order matters, so we use permutations. We compute 40p3, which equals 40 factorial divided by 40 minus 3 factorial. This simplifies to 40 multiplied by 39 multiplied by 38. The total number of possible outcomes in the sample space is 59,280. Thank you for watching.